Hello everyone and welcome back to the third video in this recursion series. And in our quest to conquer recursion, we'll be solving another easy problem which will be Fibonacci number. And this is probably the last easy problem that we'll be solving. Beyond this, we'll solve some medium and hard problems just to get a better understanding. But to cement our fundamentals and basics, I thought it'll be good to solve another easy problem. So let's understand what are Fibonacci numbers. So basically it is a sequence wherein the current number is actually the sum of the preceding two numbers. So as you can see that each number is the sum of the preceding two ones. And it starts from 0 and 1. So it is something like that the first term of this sequence is 0, the next term is 1, then these are kind of the base cases, and the next term is basically the sum of the previous two. So 0 plus 1, this will be the third term, the fourth term will be 1 plus 1 2, so on and so forth. So basically the question says that given n, we have to calculate the nth term. So if we are calling this as the 0th term, then we have to calculate the nth term. But if we refer to this as the first term, then we have to calculate the n plus nth term. So that is the question. The question is very simple. And if you see the formula for calculating the Fibonacci terms, so we can say that ये चीख चीख के कह रहा है कि this is a recurrence relation because the answer for n depends on the sub-problems of n minus 1 and n minus 2. Once we have calculated the answer for our sub-problems, then we can simply return the answer. We can add those two answers and return the answer for n. And to make it even more easier and to make it even more clear, we don't even have to think about the base cases in our question. The base case is already given, that f of 0 is equal to 0 and f of 1 is equal to 1. Now this question can be solved iteratively, but since this is the recursion series and uh, it was very easy for us to identify that this can be solved using recursion just by seeing whatever was given in the problem. The formula was nothing but a recurrence relation itself. So that's why I think recursion also makes sense here. Now, once we have identified that why can it be solved recursively and we have got our recurrence relation, let's try to draw the next obvious step is that we'll try to draw a tree. So in our tree, the first node will be n, and let's assume that we are drawing a tree for n equals to 5. Now to calculate the answer for n equal to 5, we have to calculate the answer for n equal to 4 and n equal to 3. Once we have the answer for n equal to 4 and n equal to 3, we'll be able to calculate the answer for n equal to 5. Again, for this, we'll calculate n equal to 4, we'll have to calculate 3 and we have to calculate 2. And for 3, we have to calculate 2 and 1. So you can see that 1 is a base case, so we won't be calculating for it and we can simply return from here. 2 will be further calculated and we'll be calculating 0 and 1. Again for 2 we'll be calculating 0 and 1, and for 3 we'll be calculating 2 and 1, and for 2 we'll be calculating 1 and 0. So all these are base cases, so we'll not be calculating anything for them and we'll simply be returning the answers from here. Right, so this is the recurrence tree. So now one obvious thing that we should take a moment and notice here, there are few terms which are being calculated again and again. So if you see, the second term has been calculated multiple times here. We have calculated for n equal to, we have calculated the answer so many times. So this is the one of the issues which makes the time complexity for basic recursion very bad, because these sub problems are calculated again and again, and it's a well-known problem which is known as a repeating sub problem issue. And this is exactly where dynamic programming comes into picture. So dynamic programming is a paradigm to make this process more efficient by not calculating these subproblems again and again. In dynamic programming, what we do, once we have calculated a subproblem, we store the answer for that subproblem, and if we land on that subproblem again, we do not draw the whole tree from there, we just return the answer. So just giving a heads up that the time complexity for this solution will be really bad. It can be improved a lot, but that we'll cover in detail in the dynamic programming series. So it's just a heads up here. So let's try to calculate the time complexity for a current solution. So we have already learned that calculating the time complexity using a recursion tree is nothing but actually trying to calculate the approximate number of nodes that are going to be in my tree. So let's try to identify the height of the tree. So the maximum height of the tree, if you see that in every level n is at least being decreased by 1. So here n was 5, in here the maximum value of n is 4, in this the maximum value of n is 3, and in this 2. So if you see in every level the n is at least being decreased by 1, so the maximum height that this tree can gain is obviously going to be n. And also you can see that from each node you'll have a maximum of 2 branches. So either that will be a base case and there will be 0 branches, or you'll be having 2 branches. So if we assume the worst case that there are going to be 2 branches at every level, so on the first level there's going to be only 1 node, on the second level there are going to be 2 nodes. Each of these 2 nodes are going to give rise to 2 branches each, so there will be 4 nodes here. Similarly, each of these in worst case are going to give rise to 2 branches, so they're going to be 8 nodes here. But in this case this was a base case, so we did not have 2 branches. So if I say that what are going to be the total number of nodes, it is going to be something like 1 plus 2 raised to power 1 plus 2 raised to power 2 plus 2 raised to power 3 till 2 raised to power n. Now this is a very common GP, and we can very easily say that the sum of this GP is approximately going to be equal to 2 raised to power n. So if the total number of nodes are approximately going to be equal to 2 raised to power n, it's actually going to be less than 2 raised to power n. So if you see, we assume the base case, but in certain levels there are going to be much less nodes because we do not expand the base cases further. So if we have to give a tight complexity bound, then we are going to say that the big O of big O complexity of this whole solution is actually going to be big O of 2 raised to power n. Now that we have seen the problem, we have drawn the recursion tree, and we have also calculated the time complexity, let's try to code the solution. And as I'm coding the solution, I'll also keep explaining the intuition that I'm following. So the very first step in our two-step intuition is that we'll assume that we'll solve the smaller problems, and the smaller problems simply give me the right answer. So the smaller subproblems is basically n minus 1, and the other smaller subproblem is basically n minus 2. So I know I have to assume that this method actually works for the smaller subproblems, and I don't have to worry about that. Now that I have answer for my smaller subproblems, what is going to be the current answer? So it is nothing but if I have the answer for the smaller subproblems, I just need to add those two smaller answers and I will have my current answer. So I can simply return this answer because this is going to be my current answer. And I had to do nothing for the smaller subproblems. I just need to assume that this method somehow works for my smaller subproblem. The second step in the intuition is that we hard code the base cases. So base cases are already given to us, that if n equal to 0, we return 0. If n is equal to 1, we return 1. So we have actually this was as simple as it could get. So using our two-step intuition, we have written the answer. Let's try to submit this question. So you can see that we have got the right solution, and you might want to notice that actually the runtime complexity is not as good. It is only greater than 17%, because as I told, due to the repeating sub problems, the complexity is really bad, and we can really optimize it using DP approach. So that's about it, guys. I think we have discussed everything related to this problem. Now moving ahead, we'll be discussing some better problems, the medium and hard level problems. And till then, take care, guys. Keep learning. Bye.